Okay, let's give you guys some more practice. So here, show that this function only has one zero, one and only one zero, from minus infinity to zero. Okay, so try to understand what's going on first before you jump in and try and solve the problem. Sketch it, just to get an idea of what's going on. So at the moment you've got this block plus this block plus this block here. If you look at this block here will look something like this. Y equals x 1 over x squared will look something like this. Okay, and then if you look at this block here, it looks something like this. When x is big, it wants to do this. When x is small, it wants to do this. You see, this 4 here is near x being very small. This block here will dominate this block here, so you can pretty much ignore this block here. So when x is small, it wants to do this. When x is big, it wants to do this, because you've got one block plus another block here. So this thing here will look, the graph here will look something like this for when x is small. Okay, and when x is big, it wants to do this cubic here. Okay, so your graph will probably end up looking something like this. Okay, so the point here is that show that this function here only has one solution. Well, according to our sketch, it only has exactly one solution here in the region of minus infinity to 0. Okay, so in this region here, it only has one solution here, 1 0 here. Well, anyway, show that this only has 1 0. Use the mean value theorem. Okay, so press pause and have a go. Okay, so to do this, differentiate it. It will give you, so differentiate this. It will then give you this. It will then give you this. Okay, because hang on. So when you differentiate this, maybe rewrite this as 6 times x to the power of minus 2. Okay, this, so now you can differentiate it. So this becomes 6x squared. This becomes, well, this blah blah blah. Minus 12 x to the power minus 3, and then you a constant here. So when you differentiate this, it will give you this. Okay, it will give you this. So now tidy up. It will then give you, tidy this up. It will then give you this. Okay, now if you look at the derivative in this region here, if you look at the derivative, it's the derivative is always positive, because in the region of minus infinity to 0, well, x squared here, don't forget, in the region, so in the region of minus infinity and 0 here, in this region here, what you're putting in will be a negative number. So negative number squared, it will give you a positive number. And then if you look at this here, if you put a negative number into here, this thing here will be negative, and then making this negative, and then, well, you take the negative up here, and then you take it out here. So basically, it will become plus a positive number. Think about it. The point is that in the region of minus infinity to 0, in this region here, this whole thing here will be positive. Think about it, because this, when you square it, it will be positive. This thing here will be a negative number. So take the negative out, and then, well, the whole thing here will be a positive number. Okay. Well, in this region here, the derivative will always be positive. Now, if the derivative is always positive, then it would imply, hang on. So when you get to this stage here, realize that f prime of x will always be positive, will be greater than 1 in this region here. Okay, when x belongs to this region here. So the derivative, what this statement is really saying is that the derivative will always be greater than 0 in this region here. Well, if the derivative is greater than 0, it would imply that the original function will always be climbing, will always be increasing. So in this region here, our function, because because f prime is greater than 1, it must imply that the original function must always be climbing. Now, if the original function is always climbing, then all you need to do is detect 1 point above 0 and then 1 point below 0. Now, because it's always climbing, it can only have one solution. It's never going to do this here, because here f prime would decrease. But we've just discovered that f prime is always increase. F prime is positive. So because we just discovered that f prime is greater than 1, it would imply that the original f of x must always be climbing. So this cannot be true. The point is that because this thing here is greater than 0, f of x must always be climbing. Now, if f of x is always climbing, then try to detect a number above 0 and a number below 0 here, and then it will, because f of x is always climbing, it can only have one solution. Okay, so all that we know so far is that f of x is climbing, is always climbing in this region here. Okay, so now our next step is to detect 1 point above and 1 point below, and then we know for sure that it must be that there must only be one solution. So the next step is to detect 1 above and 1. So play around. Let's randomly guess minus 1. So this is our original function here. Let's try and put minus 1 into this thing here. If minus 1 doesn't work, then try minus 0.0000001. Try that, but let's try minus 1. Put minus 1 into the original function, it will give you 8. So looking at our function here, in the negative realm here, this here is 8. Okay, and then try minus 2. If minus 2 doesn't work, try minus 9999999, whatever here. Okay, let's try minus 2. Minus 2 gives you this, minus this, plus this, whatever it may be. It's going to be a negative number because this thing here is pretty big. Then you take away a small bit, and then you add another small bit. Well, the overall answer, whatever it may be, it will be a negative number. So what we know so far is that, well, when it's 1 here, this thing here will be 8. Okay, so this bit here will be 8. When it's minus 2 here, this thing here will be this, whatever this negative number is here. It will be, well, it will be a negative 1 here. So we know we've got 1 point above, 1 point below, and because we know the original f of x is always climbing, there can only be one solution. It would never do this because f prime of x is greater than 0. So it would never do this. Okay, the original function must always be climbing. Therefore, you only have one solution. Okay.